Tonight, we're going to explore something that sounds like a simple number, but turns into one of the most brutal journeys a human being could attempt. 1 light year. You'd assume the hard part is speed, building an engine fast enough to get there. It isn't. The hard part is everything speed brings with it. Forces the human body was never built to handle, and a ship that has to survive conditions most engineering was never designed for either. And every one of those problems gets worse the longer the journey continues. By the end of tonight, you're going to understand exactly what 1 light year actually demands, and why the distance itself is only the beginning of the problem. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the number. 1 light year is 5.88 trillion miles. That is the distance light travels in a single year, moving at 186,000 miles per second. Nothing in nature moves faster than that. Not particles, not energy, not information. That speed is not a record waiting to be broken by better engineering. It is a hard boundary written into the structure of the universe itself. The universe set that limit at the moment of its creation, and it has held across every scale we've ever been able to test. So, 1 light year is the distance you'd cover if you could travel at the absolute maximum speed the universe permits, sustained for an entire year without stopping. That's the scale of what we're dealing with before we've even climbed aboard. Here's what 1 light year actually represents in terms of our own solar system's scale. Most people picture the solar system as ending just beyond Neptune. Neptune orbits at about 30 astronomical units from the Sun. But the solar system doesn't end there. Not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy objects extending from about 30 to 50 astronomical units. Pluto is a Kuiper Belt object. So are Eris, Makemake, Haumea, and thousands of smaller bodies. The Kuiper Belt gives way to the scattered disk, a sparse region extending to several hundred astronomical units. And then, much further out, the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies surrounding the entire solar system. Its inner edge is estimated to begin somewhere around 2,000 astronomical units from the Sun. Its outer edge extends to perhaps 100,000 astronomical units, possibly further. This is the region that long-period comets come from bodies with orbital periods of hundreds or thousands or millions of years. Perturbed by gravitational encounters with passing stars and sent tumbling inward toward the Sun on elongated orbits. When we watch a spectacular comet arc across the inner solar system, it has typically fallen from the Oort cloud, a journey that took it from perhaps 50,000 astronomical units down to within a few astronomical units of the Sun. 1 light year in astronomical units is 63,241 astronomical units. This puts the outer edge of the Oort cloud at roughly 1 light year from the Sun. The solar system doesn't end at Neptune. It doesn't end at Pluto. Its gravitational influence and the population of bodies bound to it extends to approximately 1 light year. The first light year of any interstellar journey is, in a real physical sense, the crossing of our own solar system's outermost territory. You wouldn't cross it and arrive somewhere new. You'd cross it and arrive at the boundary between our Sun's domain and the true void. At the outer edge of the Oort cloud, looking back, the Sun is still the brightest object in the sky. Still clearly identifiable. Still gravitationally dominant over everything around you. But distant. 63,000 times further than Earth is from the Sun, a point of light, not a disk. And looking forward in any direction that isn't toward our own star, the nearest stellar systems are still more than 3 light-years away. The void between us and them is neither our home system nor their home system. It belongs to no star. It exists because stars are rare and space is vast, and the universe was built at those proportions. Now, take a breath. Because the question isn't just how far 1 light-year is. The question is, what actually happens to you if you try to cross it? What happens to time? What happens to your body? What the ship around you is experiencing at every moment? What the universe looks like from inside something moving fast enough to matter? The answers are strange. Some of them are genuinely disturbing. And none of them are intuitive, because nothing in everyday life prepares you for velocity at a meaningful fraction of the speed of light. Your brain evolved on a planet where the fastest things moved at a few miles per hour, and the physics relevant to survival was entirely Newtonian. The universe beyond that is genuinely alien, and traveling 1 light-year is an encounter with that alien physics on every level simultaneously. The first thing to establish is speed. If you're going to travel 1 light-year, you need to pick a velocity and commit to it. Your choice of speed changes everything. The duration of the journey, the physical dangers, the warping of time, the energy requirements, the radiation exposure. The forces on the hull, everything scales with how fast you're going. Start with something we actually understand. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its peak, during close approach to the Sun, it reaches roughly 430,000 miles per hour. That is genuinely extraordinary by any human standard. At that speed, you could cross the continental United States in under 2 seconds. You could circle Earth in about 55 seconds. It is the fastest object humans have ever launched, and it is nowhere near fast enough. At 430,000 miles per hour, crossing 1 light-year takes over 15,000 years. The entire span of recorded human civilization fits inside that travel time, and still leaves more than 10,000 years remaining. 15,000 years at our fastest speed to cover 1 light-year. The gap between what we can currently achieve and what the universe requires is not a gap. It is an abyss. To cross 1 light-year in any time frame, a single human could survive. You would need to travel at a substantial fraction of the speed of light. At 10% of light speed, about 67 million miles per hour, the journey takes 10 years as measured from Earth. At 20% of light speed, 5 years. At 50% of light speed, 2 years. At 90%, about 13 months. At 99% of light speed, just over 12 months. These are the velocities where the physics starts getting genuinely strange. And strange is putting it mildly. The acceleration phase is where the physics first makes its demands clear. From the moment of departure, every second of thrust costs energy at a rate the vehicle's systems must sustain continuously. You can't simply go from 0 to 10% of light speed in a matter of hours. The forces involved at high acceleration would destroy both the ship's structure and the people inside it. A sustained acceleration of 1g, identical to the pull of gravity on Earth's surface, would be physiologically ideal for the crew. It would simulate normal gravity throughout the acceleration phase without requiring a rotating habitat. The cardiovascular system stays conditioned because it's still working against effective gravitational pull. The bones stay loaded because the crew is effectively standing in 1G. The vestibular system works normally because there's a consistent sense of up and down. From a crew health standpoint, 1G constant acceleration is the best possible scenario. And at 1G, the time to reach meaningful fractions of light speed is calculable. Reaching 10% of light speed from rest at 1G takes about 35.5 days. Reaching 50% of light speed takes about 201 days. Reaching 90% of light speed takes about 730 days. These are manageable timescales. The problem is not the duration of the acceleration. The problem is the energy it requires. For a hypothetical crewed ship of 1,000 metric tons, which is conservative for something that must carry everything its crew needs for years, sustained 1G acceleration for a year requires energy on the order of many times the total current annual energy production of Earth. That's the entire planet's electricity generation for a year, for one ship. One acceleration phase. This is not a cost that scales gradually better as technology improves. The physics does not offer a discount. The Lorentz factor requires a specific amount of energy to reach a specific velocity for a given mass. What changes with technology is efficiency, how well you convert stored energy to thrust, how much waste heat you generate, how completely you can extract energy from your fuel. Better engineering can approach the theoretical limit. It cannot exceed it. The strangeness begins with something Albert Einstein discovered in 1905. When he published The Special Theory of Relativity, among its results was one that nobody expected and that took decades to become fully accepted. Speed affects time, not metaphorically, not as a philosophical statement about the subjectivity of experience. Physically, measurably. The faster you move through space, the slower time passes for you compared to everything you left behind. This is called time dilation, and it is one of the most verified predictions in all of physics. GPS satellites orbiting Earth at about 8,000 miles per hour experience it. Without corrections for relativistic time dilation, GPS systems would accumulate position errors of several miles per day. The system would become useless within hours of operation. The correction is built into every satellite in the constellation because the effect is real and the equations are precise. Without that correction, your navigation app would be wrong by several miles by early afternoon. Particle accelerators demonstrate time dilation every single day. Muons are unstable subatomic particles with a half-life of about 2.2 microseconds. They're created in the upper atmosphere when cosmic rays strike air molecules at altitudes of about 9 miles. At the velocities, muons travel very close to light speed. They should decay long before reaching the ground, given how short their half-life is and how far they have to travel. Simple multiplication says they should be gone before they get anywhere near sea level. They aren't. On Earth's surface, they're still present in numbers that only make sense if time has slowed for them during the journey down. It has. The Lorentz factor predicts exactly how many survive the trip. The prediction matches observation every single time experimenters have checked. This is not interpretation. This is a number and a measurement that agree to the precision of the instruments used. And if you're traveling 1 light year at relativistic speed, time dilation is not a footnote in the physics. It is the defining fact of your existence aboard that ship. Einstein's insight in 1905 came from asking a question that sounds simple, but had never been answered properly. What does it mean for two events to happen at the same time? If you're standing still and two lightning bolts strike the ground a few hundred feet apart, and both strike simultaneously from your perspective, does someone moving relative to you agree that they were simultaneous? Newton's physics assumed yes. Of course, they're simultaneous. Time is time, the same for everyone. Einstein showed the answer is actually no. Two events that are simultaneous for a stationary observer are not simultaneous for an observer moving relative to them. The simultaneity of events is not absolute. It depends on the observer's state of motion. This isn't a philosophical statement about perception. It's a physical statement about the nature of time. Time is not a single universal river running the same rate everywhere. It is a local property of the observer. Each object, each person, each clock carries its own version of time, and those versions run at rates determined by how fast that object is moving and how deep it sits in a gravitational field. The consequence for travel is that two clocks, synchronized at the same location and then separated, one staying put, one moving at high velocity, will no longer agree when they're reunited. The moving clock will have logged fewer seconds. This has been confirmed with atomic clocks on aircraft. The clocks flown around the world tick slightly slower than the ones left on the ground. The difference is tiny nanoseconds. But it is real, it is measurable, and it matches the prediction of special relativity exactly. Scale that experiment to a ship crossing 1 light year at 99% of light speed, and the difference is not nanoseconds. It is weeks. The physics is the same, only the scale is different. Here is how the numbers actually work. There's a quantity physicists call the Lorentz factor. It describes how much time slows for a moving object relative to a stationary observer. At everyday speeds, a car on a highway, a commercial jet, even a rocket to the space station, the factor is so close to 1 that the time difference is a few nanoseconds over a lifetime of movement. Completely immeasurable, without atomic clocks. Irrelevant to your daily existence in every practical sense. But as you approach the speed of light, the factor climbs. At 10% of light speed, it's barely above 1.005. Time passes about 0.5% slower for you than for stationary observers. Real, but small. At 50% of light speed, it's about 1.15. For every year you experience, 1.15 years pass on Earth. Not dramatic yet, but growing. At 90% of light speed, the factor reaches approximately 2.3. For every year you age aboard the ship, 2.3 years pass outside it. At 99% of light speed, it jumps to about 7.1. For every 7 years that pass on Earth, you personally live through one. At 99.9% of light speed, the factor reaches approximately 22. For every year you experience on board, 22 years pass everywhere else. This has a concrete consequence for a 1 light-year journey. A ship traveling at 99% of light speed takes about 1 year and 13 days to cross 1 light-year. Measured from Earth, that's what an external observer on Earth would measure. But for the crew inside the ship, with the factor at 7.1, they age only about 7 weeks. They launch. They cross 5.88 trillion miles of empty interstellar space. They arrive at their destination, and they have personally experienced about 52 days. Meanwhile, back on Earth, over a year has passed. Families are older. Events have occurred. The world has moved forward at a rate completely independent of what was happening aboard that ship. This isn't approximation. This isn't a philosophical thought experiment about subjective time. It is what the equations predict, what every experimental test at every accessible scale confirms, and what would actually happen. The universe keeps separate clocks for things moving at different speeds. Velocity is the dial that controls how far those clocks diverge. And the divergence, once it has occurred, is real and cannot be reversed. You cannot go back and resynchronize. You've lived different amounts of time. That's the situation. The precision of the Lorentz factor deserves a closer look. Not because it's an impressive number, but because of what that precision implies. The factor isn't approximate. It isn't a rough guide. It is an exact mathematical relationship that has been verified at every velocity and energy scale, accessible to experiment. When a muon survives its journey through the atmosphere longer than its half-life should allow, the Lorentz factor predicts exactly how much longer it survives. Not approximately. Exactly. When atomic clocks are flown on aircraft and compared to clocks left on the ground, the time difference is exactly what the Lorentz factor predicts. When particle accelerators measure the behavior of particles moving at 99.999% of light speed, the particles behave exactly as the Lorentz factor says they should. The agreement between theory and measurement across 9 decades of experimental physics is not suggestive. It is definitive. The physics is not a model that might be superseded. Special relativity is as tested and confirmed as any scientific theory we have. The only scientific framework more thoroughly tested is quantum mechanics, and the two frameworks agree with each other in every domain where both apply. This matters for the journey we're describing, because it means we're not extrapolating from a theory that might be wrong. We're applying a confirmed physical law to a new set of conditions. The numbers for a 1 light-year voyage, the 52 days of crew, aging at 99% of light speed, the year plus of Earth time, are not predictions that might turn out differently when tested. They are the results of applying verified physics to the specific parameters of the voyage. The universe has already told us how time behaves at those velocities. We know the answer. We just haven't made the journey yet. Now, step inside the ship and consider what the journey actually looks like from there, because it is nothing like flying through space in any film you've ever watched. The visual experience of high-velocity interstellar travel is deeply alien in ways that are completely described by known physics. We don't need to speculate about what you'd see. We can calculate it. The first visual effect is the Doppler shift. You've encountered this with sound. A vehicle approaching you has its engine noise compressed to a higher pitch. As it passes and recedes, the pitch drops. The sound waves are compressed ahead of the vehicle's motion and stretched behind it. Light behaves the same way, because light is also a wave. When you're moving toward a light source at a significant fraction of the speed of light, the wavelengths of that light are compressed. The light shifts toward shorter wavelengths, toward blue, toward violet, and at extreme velocities, toward ultraviolet and beyond. When you're moving away from a source, its wavelengths stretch toward red and then into infrared. At 10% of light speed, the effect is noticeable but subtle. Stars in the forward direction appear slightly bluer than normal. Stars behind you appear slightly redder. The sky still looks broadly familiar. At 50% of light speed, the shift is pronounced. Stars ahead that were yellow now look blue-white. Stars that were orange-red now look yellowish. The forward hemisphere of the sky has a notably different palette than the one you knew. At 90% of light speed, the Doppler shift is extreme. Visible light from stars directly ahead has been compressed into ultraviolet frequencies, wavelengths your eyes cannot detect. Stars that were luminous and visible have effectively gone dark from your perspective. Their light shifted entirely out of your visual range. What replaces them in the visible spectrum is infrared light from cool, dim stars that were near invisible from Earth, now shifted up into wavelengths. Your eyes can register by your velocity. The forward sky is populated by different stars than the ones you knew from Earth. Stars that were invisible before. A different arrangement. A different sky. And at 99% of light speed, most of what you'd see ahead has been shifted so far into ultraviolet, and beyond that, the forward arc looks peculiar, even in terms of what light is present at all. The second visual effect is called relativistic aberration. At rest, stars are distributed across the entire sphere of the sky in roughly the pattern your star charts show. When you start moving at relativistic velocity, the geometry of incoming light changes. Stars that were off to the side appear to shift toward the direction of travel. Stars that were behind you crowd forward. The faster you go, the more extreme the crowding. At 50% of light speed, the entire night sky appears compressed toward the forward hemisphere. The rear half of the sky looks noticeably emptier than normal. At 90% of light speed, almost the entire visible stellar content of the universe has been swept into a cone spanning about 26 degrees ahead of you. Stars that should be to your left, to your right, behind you, all compressed forward by your motion. The sky in the aft direction has gone nearly black. At 99% of light speed, that cone has narrowed further. Virtually all visible starlight crowds into a tight ring surrounding a point directly ahead. Behind you, almost complete darkness. Not because there's nothing there, but because the light from everything in those directions has been bent forward by your velocity. The physics of wave propagation and motion don't care that you'd prefer the stars to stay where you expect them. They move. And it's not just starlight. The cosmic microwave background, the faint afterglow of the universe's beginning, normally spread uniformly across the entire sky at a temperature of about -455 degrees Fahrenheit. Also, blue shifts forward with your velocity. Normally, this radiation is completely invisible to human eyes. It exists in microwave frequencies, far below what you can see. But at 99% of light speed, it has been compressed into visible and ultraviolet wavelengths. The forward arc glows with it light from no particular star, but from the universe's oldest light, the relic radiation of the Big Bang itself, made visible by the speed you're traveling. Standing at the forward viewport of a ship crossing 1 light year at near light speed, what you'd see would be unlike anything any human has ever witnessed. A blazing ring of compressed light ahead. Darkness almost everywhere else. Stars you've never seen before, because they were previously in the infrared. Stars you expected to see, gone dark because their light has been pushed beyond your visual range. The universe rearranged by your velocity into something completely new. Now we have to talk about something that almost everyone overlooks when imagining interstellar travel. The interstellar medium. Space is not empty. This is one of the most important physical facts about interstellar travel, and one of the most commonly misrepresented. Between the stars, there is gas and dust. The interstellar medium. a thin distribution that fills the galaxy. On average, roughly 1 atom per cubic centimeter in typical interstellar regions. Mostly hydrogen, the simplest and most abundant element in the universe. About 10% helium by number. Traces of carbon, oxygen, nitrogen, iron, and other heavier elements, scattered remnants of stars that lived and exploded before our solar system formed. And scattered throughout, microscopic dust grains, particles of silicate minerals and carbon compounds, typically ranging from nanometers to micrometers in size. By any laboratory standard, this is an extreme vacuum. The best vacuum chambers on Earth contain several 100 million atoms per cubic centimeter. Interstellar space has one. To put that in perspective, the best vacuum we can achieve in a laboratory is still roughly 100 million times denser than typical interstellar space. Interstellar space is not just empty. It is almost incomprehensibly empty. At low speeds, this thinness is entirely irrelevant to a spacecraft. Voyager 1 has been traveling through interstellar space since it crossed the heliopause in 2012. It has been out there for over a decade. Its instruments still function. 1 hydrogen atom per cubic centimeter presents no practical problem at 38,000 miles per hour. The atoms hit the hull so rarely and with so little energy that the cumulative effect over decades of travel is negligible. That changes completely at relativistic velocity. At 10% of light speed, the kinetic energy of a single hydrogen atom striking the bow of your ship, measured in the ship's reference frame, is approximately 400 million electron volts. This is the energy range of high-energy cosmic ray particles. The same particles that space agencies worry about when planning long-duration missions. At typical interstellar densities, the bow encounters on the order of several hundred atoms per second per square meter of frontal area. Each collision, individually, deposits a small amount of energy. But collectively, over months and years of travel, those collisions accumulate. They heat the hull material. They create radiation damage in the molecular bonds of whatever the hull is made of. They produce secondary particles, fragments from disrupted atomic nuclei that propagate deeper into the material. Over a 10-year voyage at 10% of light speed, the cumulative fluence of hydrogen atoms hitting the forward shield would be enormous. The material damage would be real and would require the shield to be designed specifically to handle it. At 90% of light speed, the situation becomes severe rather than manageable. Each hydrogen atom the ship encounters now carries, relative to the ship, about 1,200 million electron volts of kinetic energy. That is the energy range of protons produced by large research synchrotrons, particle accelerators, that were pushing the frontier of physics in the mid-20th century. At 99% of light speed, the energy rises further still, into ranges that approach the most powerful accelerators ever built. A ship at 90% of light speed is flying nose first into a continuous, low-flux version of that particle beam. The interstellar hydrogen atoms, from the ship's reference frame, are accelerated to near light speed. The hull doesn't know whether it's a fast proton hitting a stationary wall or a stationary wall hitting a fast proton. These are physically identical situations, and the damage at those energies is not negligible. High-energy protons striking metal can shatter atomic nuclei, producing cascades of secondary particles, neutrons, pions, heavier nuclear fragments, gamma rays that propagate outward through the shielding material. If secondary particles reach the crew compartment, they deposit energy in biological tissue. The shielding required to protect crew members from the interstellar medium at 90% of light speed would need to be substantial. Meters of dense material at the leading edge of the ship. Water is among the better practical choices. Hydrogen nuclei absorb high-energy particle energy more efficiently without generating as many damaging secondary particles as metals like aluminum or iron do. The issue with water is mass. Meters of water is a very large amount of mass, and mass, at relativistic velocity, is the central problem that everything in interstellar travel design returns to eventually. The energy required to move mass to relativistic speeds is one of the most important physical facts about interstellar travel, and one of the most consistently underestimated. The relationship is not linear. At everyday velocities, kinetic energy scales roughly as 1/2 times mass times velocity squared. Large for large velocities, but growing in a way that's at least intuitively graspable. As you approach the speed of light, the relationship changes fundamentally. The energy required to gain additional velocity grows according to the same factor that dilates time, the Lorentz factor. This factor accelerates toward infinity as velocity approaches the speed of light. At 50% of light speed, you need to supply energy equivalent to about 15% of the ship's rest mass energy to get it moving at that speed. At 90% of light speed, you need about 130% of the rest mass energy. Rest mass energy is the energy equivalent of the ship's mass. From Einstein's equation, E equals mc squared. E equals mc squared says that mass and energy are interchangeable. The energy equivalent of 1 kilogram of mass is approximately 90 petajoules. That's roughly 21 megatons of explosive equivalent. To accelerate 1 kilogram of anything to 90% of light speed requires supplying energy equal to about 117 petajoules. For a ship large enough to carry a crew with life support, radiation shielding, food, water, medical supplies, navigation systems, communication equipment, spare parts, the total mass would be at minimum several thousand kilograms, likely much more. Each kilogram costs roughly 117 petajoules to accelerate to 90% of light speed. And then you need to decelerate at the destination. Same cost again. The most energetically dense fuel conceivable is antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate completely and totally. 100% of their combined mass converts to energy, exactly as E equals mc squared describes. 1 kilogram of antimatter annihilating, with 1 kilogram of ordinary matter releases about 180 petajoules. Nothing in all of physics can match this energy density. It is the theoretical ceiling, the absolute maximum energy available from any given mass of fuel. And even with perfect antimatter fuel, the mass ratios for a crewed interstellar ship at high relativistic velocity are punishing. The Tsiolkovsky rocket equation, first published in 1903 by Russian mathematician Konstantin Tsiolkovsky, and as unforgiving now as it was then, describes the fundamental relationship between propellant mass and the velocity change it produces. For relativistic velocities, the relationship compounds. To accelerate a ship carrying even 1,000 kilograms of useful payload to 90% of light speed and then stop it again at the destination, you need far more than 2,000 kilograms of antimatter, because you have to accelerate the fuel too. And the fuel for the fuel. The rocket equation compounds the way compound interest compounds, except much faster and in the wrong direction for your mass fraction. The result is that the vast majority of the ship's mass at launch would need to be fuel. A small fraction would be the actual payload, the people, and the equipment they need to survive. And we cannot produce antimatter in any quantity approaching what this would require. The combined output of all particle accelerators on Earth generates nanograms of antimatter per year. A nanogram is 1/1000th of a gram. An interstellar mission using antimatter fuel would require kilograms, possibly tons. The production gap between what we can make and what we would need is roughly 10 orders of magnitude. That is not a gap engineering can bridge with incremental improvements. That requires physics we don't currently have, at scales we can't currently achieve. The universe does not provide shortcuts. Either the energy exists or the journey doesn't happen. Consider what Project Orion tells us about this gap. In the late 1950s and early 1960s, the United States government funded serious engineering work on a propulsion concept that sounds extreme until you realize it was based entirely on existing technology. The idea was to propel a spacecraft by detonating nuclear bombs directly behind it. A massive shock absorber plate at the aft end of the ship would capture the impulse from each explosion. Several explosions per second would accelerate the vehicle. The bombs existed. The shock absorber engineering was worked out. Freeman Dyson, one of the most formidable physicists of the 20th century, calculated trajectories and performance in detail. Project Orion was not fringe science. It was a serious engineering effort conducted by serious physicists and engineers using real hardware and real calculations. Large Orion vehicles could theoretically reach several percent of light speed. Not a meaningful fraction of what interstellar travel requires, but a real, substantial improvement over anything built before or since. The project was ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Not by physics. Not because the concept didn't work. By policy. Orion is a data point. It shows that the gap between what we can build today and what interstellar travel requires is not absolute. Every serious interstellar propulsion concept that has been rigorously evaluated, Orion, Project Daedalus, laser sails, magnetic sails, identifies real physics that could in principle provide meaningful performance. None of them are ready. None of them approach the full requirements. But they are all pointing in the same direction, toward the physics that works, away from what doesn't. Think carefully about deceleration, because it's the half of the problem that most discussions shortchange, and the physics is unforgiving about it. Assume you've solved propulsion. You've found the energy, built the engines, accelerated your ship to 90% of light speed. You're crossing 1 light year. You're going to arrive somewhere, and you need to stop. There is no brake that works in deep interstellar space. No air resistance. No runway. No medium to push against in any useful sense. The interstellar medium creates drag so small it's a navigational correction over years, not a meaningful deceleration force. The only way to slow from 90% of light speed is to fire your engines in the direction of travel. Thrust yourself backward against your motion and sustain that thrust until velocity drops to something manageable. This consumes the same amount of energy as the acceleration phase. If you carry fuel for both legs, the initial launch mass grows substantially. The fuel for deceleration has to be accelerated during the outbound trip, which requires more fuel to accelerate the deceleration fuel. The rocket equation compounds again. One-way missions have simpler energy budgets than return trips, which is part of why serious proposals for early interstellar missions involve one-way voyages. You only pay the acceleration cost once. But one-way means no return. The first humans to leave the solar system permanently, knowing they won't come back, accepting that as the price of going. The physics is more tractable. Everything else about it is harder. For missions that intend to stop at a destination and return, the energy cost is at least 3 to 4 times the one-way acceleration cost, accounting for deceleration and the return trip. The compounding makes already enormous numbers more enormous still. Proposals to sidestep. This include laser propulsion. A massive laser array in the home system pushes the ship outbound without the ship carrying propellant for that leg. This makes the ship lighter, and the energy cost comes from the laser installation, not from fuel aboard. But deceleration still must happen at the destination. Without a laser array at the other end, the ship carries its own propellant to stop, which adds mass, which the laser has to accelerate. The problem shifts, but doesn't disappear. Stellar light sails for braking at the destination have been proposed. For a ship of practical mass, the required sail size becomes enormous. And arriving at exactly the right trajectory and distance from the destination star to use its light for braking, after years of travel, requires extraordinary navigational precision. Every proposal has constraints. Every constraint has consequences. Physics charges a fee for crossing interstellar distances, and the fee is not negotiable. In 1978, the British Interplanetary Society published the Daedalus Study, a 2-year engineering feasibility study for an unmanned interstellar probe. The target was Barnard's star, about 6 light-years away. The proposed vehicle would use inertial confinement fusion, small pellets of deuterium and helium, 3 compressed to fusion by electron beams, triggered 50 times per second. The vehicle would reach 12% of light speed. The one-way trip to Barnard's star would take about 50 years. The mass budget, around 54,000 metric tons at launch. The engineering challenges were enormous. The helium. 3 requirements alone, fuel for the first stage, would require mining the atmosphere of Jupiter. Not because the designers were being unrealistic, because the physics requires it. That's how much fuel a fusion drive needs to push 54,000 metric tons to 12% of light speed. The Daedalus study is notable, not because it solved the problem, but because it characterized it. It showed, with rigorous engineering calculation rather than vague speculation, what the requirements actually are. The Icarus Interstellar project, started in 2009, continued that work. The Breakthrough Starshot Initiative, funded in 2016, targeted a different approach. Entirely tiny light sails, propelled by a ground-based laser array, to 20% of light speed, in recognition that the mass problem is the central problem. Make the spacecraft small enough, and the energy requirements drop from impossible to merely extremely difficult. Each of these is a different engagement with the same physical constraints. Different proposals, same constraints. The constraints don't change. What changes is how seriously people try to work within them. Set the energy problem aside. Assume it's solved. The ship is moving. You're crossing 1 light-year at a substantial fraction of light speed. Now, the human body has its own separate and serious objections. The human body evolved over millions of years to function in one specific set of conditions. One gravitational field, roughly 9.8 meters per second squared, the pull of a rocky planet with Earth's mass. One atmospheric pressure, about 101,000 pascals at sea level. One radiation shielding environment provided by Earth's magnetic field and several dozen miles of atmosphere above your head. Every system in your body, skeletal, muscular, cardiovascular, neurological, immunological, hormonal, sensory, was shaped by millions of years of evolution in those conditions. Remove them, and the systems adapt. But biological adaptation doesn't mean improvement. It means optimization for the new environment. And the new environment is not the one your biology was built for. Start with gravity. In a ship coasting at constant velocity through interstellar space, there is no effective gravity. Everything floats. This feels unusual for a few minutes and pleasant for a few hours. Over days and weeks, it begins to become a systematic dismantling of your body. Bone is not dead, structural material like steel or concrete. It is living tissue in constant dynamic remodeling. Specialized cells, called osteoblasts, build new bone by depositing calcium phosphate mineral into a protein matrix. Other cells, called osteoclasts, break bone down, dissolving the mineral back into the bloodstream. On Earth, mechanical stress from standing and walking provides the signal that tells osteoblasts to maintain their pace, to keep building bone at the rate it's being broken down. Without that signal, the balance tips. Osteoclasts continue their work at the normal rate. Osteoblast activity slows. Bone density falls. The rate is roughly 1 to 2% of mineral density per month in the most affected regions. The weight-bearing bones of the spine, the hips, the upper leg. Astronauts on 6-month International Space Station missions lose an average of 10 to 15% of their bone mineral density. Their skeletal systems are measurably weaker after half a year. Not metaphorically weaker. Measurably, quantifiably weaker in ways that show up on bone density scans. Recovery after returning to Earth takes many months of weight-bearing exercise and physical therapy. Some density loss never fully recovers. The skeleton has adapted to a new baseline, and the old baseline is only partially retrievable. Now, extend that 6 months to the years that a 1 light-year journey at 10 or 20% of light speed would require. 10 years at 10% of light speed. The people who would have to find out are the ones inside the ship, years from anyone who could help, in a medical situation that has no established treatment protocol. We might be wrong about the extrapolation. The biology might plateau, but we don't know. And that uncertainty, at the distances and timescales of interstellar travel, is a serious problem. Muscle follows identical logic. On Earth, simply being upright requires continuous low-level muscular work. Your postural muscles, the deep muscles of the back, the core, the legs, fire constantly to keep you from collapsing. Walking, sitting, standing, shifting weight, all of these engage muscle chains that maintain strength and mass. In microgravity, that demand disappears. The muscles that evolved to work against gravity have no load to work against. They atrophy rapidly. International Space Station, astronauts follow mandatory daily exercise protocols, 2.5 hours of structured resistance training, and cardiovascular exercise every single day. Not optional. Not recommended. Required by mission rules. And despite that mandatory 2.5 hours, they still lose up to 20% of muscle mass over a 6-month mission. The exercise slows atrophy. It cannot stop it. The body continuously optimizes toward the actual environment it's in, and the actual environment is one where muscles don't need to be as large or as strong. Over years, the accumulated adaptation deepens. Muscles that remain restructure toward endurance performance in zero gravity rather than toward the load-bearing, high-force output needed in a gravitational environment. Returning to gravity after years of this is not simply a matter of doing physical therapy for a few weeks. It would require rebuilding from a state that has no established rehabilitation protocol. The cardiovascular system adapts to microgravity in ways that are equally problematic and perhaps more insidious. On Earth, the heart pumps blood upward against gravity to reach the brain. This is not a trivial task. The brain sits about 18 to 20 inches above the heart. Getting blood there requires the heart to generate enough pressure to overcome gravity across that distance. In microgravity, there is no upward. Blood doesn't pool in the legs as it normally does. Fluid redistributes toward the head and chest, a condition astronauts often describe as feeling like they have a permanent head cold, with puffy faces and nasal congestion. The body, sensing elevated pressure in the upper body, interprets this as excess fluid and begins excreting it. Blood volume decreases. The heart, no longer fighting gravity to reach the brain, doesn't need to work as hard. It adapts over weeks and months, becoming somewhat smaller, remodeling toward a less stressful workload. This adaptation is appropriate for the environment the heart is actually in. But it's the wrong adaptation for a return to gravity. Astronauts returning from 6-month missions frequently need assistance leaving the spacecraft. Their cardiovascular systems have deconditioned to the point where suddenly having to pump blood upward against gravity again is a shock. Standing causes blood pressure to drop. The brain doesn't get adequate perfusion. People faint. Reconditioning takes weeks of gradual re-exposure. After years of microgravity, the deconditioning would be far more profound. The longest continuous spaceflight on record is 437 days by Russian cosmonaut Valery Polyakov aboard the Mir space station. An interstellar voyage at 10% of light speed takes a decade. That's more than 8 times longer than the longest anyone has ever been in microgravity. Whatever happens to cardiovascular health over that timescale, we're extrapolating into unknown territory. Vision changes in ways that weren't fully appreciated when space medicine was in its early decades. About 60% of astronauts who spend extended time aboard the International Space Station report visual changes after their missions. Many of these changes are subtle. Some are significant. A few are permanent. The leading explanation involves intracranial pressure, the pressure of fluid surrounding the brain and optic nerves. Without gravity pulling fluid toward the feet, the normal downward distribution of cerebrospinal fluid changes. More fluid accumulates around the brain and optic nerves than would normally be there in a person standing upright. The elevated pressure can cause swelling of the optic disc, the point where the optic nerve meets the retina inside the eye. It can also subtly deform the eyeball itself, changing its focal length. The most common result is a shift toward farsightedness. Some of this reverses after returning to Earth. Some doesn't. There are astronauts with permanently reduced visual acuity following 6-month space missions. Over years of elevated intracranial pressure, the accumulated damage would be greater. And compromised vision on an interstellar ship is not a minor inconvenience. Identifying problems in systems requires seeing them. Reading instrument displays requires seeing them. Performing delicate repairs in confined spaces requires seeing what you're working on. The crew's ability to keep the ship functioning and to keep themselves alive depends on them being able to see what they're doing. The immune system changes in microgravity as well, and the changes are not in a useful direction. Studies have shown that immune cells exhibit reduced functional capacity in microgravity. Their proliferation is impaired. Their ability to recognize and respond to pathogens is diminished. Several viruses that healthy immune systems normally keep suppressed show signs of reactivation in astronauts on longer missions. Epstein-Barr virus, which causes mononucleosis and is present in the majority of adults in a dormant state. The varicella-zoster virus, which causes chickenpox initially and then remains dormant, capable of reactivating as shingles. Cytomegalovirus, another herpes family virus that stays latent in most infected people. In astronauts, these viruses become detectable at elevated levels in saliva and other body fluids during missions. The immune system is suppressing them less effectively. Over a multi-year voyage, in a small crew living in a closed and self-contained habitat, this immune suppression compounds over time. Any illness that develops encounters immune systems running below their design capacity. Any pathogen from the crew's own dormant viral reservoirs that reactivates encounters less effective resistance. And medical care is whatever was brought on the ship. There is no hospital. There is no physician outside the crew, no specialist to evacuate to. Every medical event is managed with the training and supplies aboard. With communication delays of months to years for any advice from Earth, the medical challenge of an interstellar voyage is not just that space is hostile, it's that you face the consequences of that hostility with very limited resources and no possibility of external help. The psychological dimension of an interstellar voyage is a challenge that parallels the biological ones, and it is no less severe. Human beings evolved in social environments. Our ancestors lived in groups. Survival depended on community, on the exchange of resources, information, and support that only groups provide. Our psychology is calibrated for a world with other people in it. Remove that environment, and human psychology responds. Not catastrophically in every case, but measurably, reliably. The research on isolated and confined environments, Antarctic winter overstations, submarine crews on long patrols, space station crews gives a consistent picture of psychological shifts over time. Mood destabilizes over extended isolation, interpersonal conflicts, which in normal social environments are diffused by the presence of many people and the ability to seek different company, concentrate and intensify in small groups with no exit. Cognitive functions associated with emotional regulation can become less effective over months of confinement. Performance on tasks requiring sustained attention degrades in ways that are statistically significant. Sleep quality tends to deteriorate in isolated and confined environments, particularly when natural light cycles are absent or disrupted. And the particular character of interstellar isolation adds dimensions that Antarctic or submarine isolation doesn't have. Communication with home degrades continuously. It's not simply that contact is limited from the start. The connection actively worsens. Every month, the signal delay grows. Every month, what arrives from Earth is older. The crew watches. In real time and in slow motion, the communication link to everything they knew attenuate toward uselessness. 6 months into the voyage, Earth's responses arrive weeks after the questions were sent. A year in, it's months. At 5 years in, the delay is half a year each way. Nothing happening on Earth now can be known aboard the ship for 6 months. The world they left continues without them, in ways they can only learn about with enormous delay. People they care about experience things, good things, and difficult things, and the crew learns about those events long after the fact. Every exchange is a conversation with the past. Consider, specifically, what communication at 1 light year means for a crew member trying to maintain any relationship with people back on Earth. You send a message. You describe what happened today, what you're thinking, how you're doing. That message travels at light speed, the fastest anything can move, and arrives at Earth a year later. The person you care about reads a description of who you were and what you experienced a year ago. They write back immediately, the same day they read your message. They describe their life, their thoughts, their current situation. Their response travels back to you at light speed. It arrives a year after they sent it. 2 years after you sent your original message, you receive a response to it. You're reading about what their life was like a year ago, written in response to what your life was like a year before that. The exchange is real. The care is real. The words are genuine. But you are both responding to each other's past selves. The conversation is always conducted in a gap. Any statement you make is about a situation that has been resolved, changed, or evolved long before the response arrives. Any response you receive addresses a you that no longer exists in quite the same form. The emotional weight of this accumulates. Not immediately. Not in the first months, when the delay is still weeks rather than years. But over the full span of the voyage, the correspondence becomes something different from communication. It becomes a form of historical correspondence. Like writing letters to someone who lived in the past and receiving their replies about your future, except it is real. It is happening in the present tense to both parties. It is just that the present tense for each of you no longer overlaps. The psychological weight of that, sustained over years, is a genuine challenge that current research on isolated environments can identify but not fully characterize. Because the delay itself is a new variable. Antarctic stations are isolated, but they can call Earth in near real time. Submarine crews are cut off during a patrol, but the patrol ends. The crew of an interstellar ship faces isolation whose defining feature is not just its duration, but its deepening. Every day, the link is a little more attenuated. Every month, a little more of a historical record than a conversation. Over years, the gap becomes the dominant fact of their relationship to Earth. And the only people who know what it actually feels like are aboard the ship. The most reliable solution to most of the microgravity problems is artificial gravity through rotation. This is not exotic technology. It's basic physics. A rotating structure creates centripetal acceleration that is physically indistinguishable from gravity to anyone standing on the inner rim. Your cardiovascular system, your skeletal system, your vestibular system, your immune system, all respond as they would to gravity. The bones get the mechanical loading they need. The heart gets the gravitational challenge it evolved to handle. The fluid distribution in the body returns to normal. The engineering challenge is making it work at the right scale and rotation rate. The human vestibular system can tolerate rotation up to about 2 rotations per minute without producing significant disorientation. Above that rate, the Coriolis effect becomes noticeable. When you move your head in a rotating environment, objects appear to curve unexpectedly. This causes nausea and disorientation in most people. 2 rotations per minute is roughly the comfortable upper limit. To produce 1 g of effective gravity at 2 rotations per minute, a rotating ring needs a radius of about 738 feet. That's approximately the length of 2 football fields, end to end. This is not physically impossible. Multiple credible engineering studies over several decades have proposed rotating habitats at this scale. The designs are complex, but not based on unknown physics. But it adds mass. Every structural element of that rotating ring is mass that the propulsion system must accelerate to the ship's cruise velocity. And mass, as we've already established, is the thing the energy problem is most sensitive to. The solution to the biology problem imposes additional costs on the energy problem. These two challenges are not independent. Solving one makes the other harder. This is the pattern that runs through all of interstellar engineering. The problems interconnect. Every solution has costs. Every cost has consequences. The universe enforces this consistency. One thing the energy calculations make relentlessly clear is the extraordinary sensitivity to mass. Every kilogram of mass aboard the ship is a kilogram that the propulsion system must accelerate to the cruise velocity and then decelerate at the destination. The energy cost per kilogram is fixed by the velocity and the Lorentz factor. It cannot be reduced by clever engineering. The only variable that engineering can meaningfully touch is how much mass is aboard. This creates a systematic pressure on every design decision. Structural materials are chosen for the highest possible strength-to-mass ratio. Life support systems are designed to be as compact and light as possible while maintaining reliability. Food and water systems that can recycle and regenerate reduce the mass of consumables that must be carried. Everything redundant that can be made non-redundant is evaluated. Every kilogram of redundancy removed from one system could allow a kilogram of additional radiation shielding, or a kilogram of additional medical supplies, or a fraction more fuel. These are genuine trade-offs, not hypothetical ones. Interstellar vehicles face a situation where reaching them from Earth is impossible, which means the redundancy must be different in character, not simply more of the same system. Genuinely different approaches to the same function, so that multiple independent failure modes would have to occur simultaneously to cause a catastrophic loss. This philosophy makes each system heavier and more complex than a minimalist design would require. It adds mass. And mass is the thing the energy equations tax without mercy. Every engineering choice on an interstellar ship is a negotiation between the cost of failure and the cost of mass. And the cost of failure, at distances where no help can arrive, is absolute. The cost of mass is also, in its own way, absolute. There is no solution that makes the trade-off disappear. There is only the skill of making it as well as possible, given what you have to work with. There is one more physical constraint that doesn't get discussed as often as it should. As you accelerate toward a meaningful fraction of the speed of light, the kinetic energy your ship carries grows to scales that have no terrestrial analog. At 10% of light speed, a 1,000 kilogram spacecraft carries kinetic energy equivalent to roughly 108 megatons. That's not the fuel aboard the ship. That's just the motion itself, the kinetic energy of the mass already moving. A failure that causes a significant structural breakup at cruise velocity doesn't produce wreckage floating in space. It produces fragments, each of which carries enormous kinetic energy, continuing on approximately the same trajectory at approximately the same velocity. Managing this risk, designing for graceful degradation rather than catastrophic failure, Ensuring that system failures cannot propagate in ways that cause structural breakup at velocity is a constraint that doesn't exist for any other form of transportation. Humans have come and engineered. You validate the design through analysis and through testing of components and subsystems at accessible velocities. You then apply those validated models to the full-scale, full-velocity scenario. The safety margin for error is not generous. Now consider radiation. In interstellar space, far from Earth, far from any stellar magnetic field, far from any atmosphere, the radiation environment is constant and arrives from every direction simultaneously. The primary threat is galactic cosmic rays. High-energy particles, predominantly protons, but also heavier atomic nuclei, stripped of their electrons, accelerated to near light speed by violent astrophysical events scattered across the galaxy and beyond. Supernovae accelerate particles at their expanding shock fronts. Pulsars, rapidly spinning neutron stars with extraordinarily intense magnetic fields, accelerate particles with those fields. Active galactic nuclei contribute particles at the very highest energies. These particles travel through the galaxy for millions of years, bouncing off magnetic field lines and magnetic irregularities, losing relatively little energy during their wandering. They arrive at any given point in space from every direction, continuously, without pause, at all times. On Earth, two shields handle this. The magnetic field deflects most charged particles before they reach the atmosphere. The atmosphere, 60 miles of air above your head, absorbs the secondary particles produced when cosmic rays do enter it. Your annual radiation exposure from cosmic rays on Earth's surface is roughly 0.3 millisieverts. Managed. Safe for a human lifetime. In interstellar space, neither shield exists. The ship's hull is all that stands between the crew and this constant particle radiation. When a high-energy proton hits an aluminum nucleus, it can shatter it. The resulting shower of secondary particles, neutrons, pions, heavier nuclear fragments, gamma rays, spreads outward from the collision point. These secondaries carry significant energy and propagate through the shielding and beyond. In some configurations, a thin aluminum hull can actually increase the biological dose inside the spacecraft. Because one incoming particle becomes many outgoing particles, each capable of causing tissue damage. This is why material choice matters as much as shielding thickness. Hydrogen-rich materials, water, polyethylene. Certain hydrogen-containing polymers absorb high-energy particle energy more efficiently without generating as many damaging secondary particles. A proton stopped by a water molecule doesn't produce the same secondary shower as a proton shattering an aluminum nucleus. Water tanks surrounding the crew compartment are among the more practical options. They provide dual-purpose radiation shielding and water storage, which helps justify the mass cost. But meaningful radiation protection requires meters of material, not centimeters. Meters. Astronauts on the International Space Station, partially shielded by Earth's magnetic field, receive 100 to 200 millisieverts of radiation per year, roughly 60 to 100 times higher than at Earth's surface. In deep interstellar space, without Earth's magnetic field offering any protection, the annual dose, without substantial shielding, would be higher still. Over years, over the decade, a 1 light-year journey at 10% of light speed requires the cumulative dose is the number that matters most. The probability of radiation-induced cancer increases with cumulative dose. more years of exposure. Higher accumulated dose, higher probability. The math doesn't allow exceptions. It just runs. High-energy cosmic rays also interact with brain tissue in ways that are distinct from lower-energy radiation. A high-energy heavy ion, a carbon nucleus, an iron nucleus, a silicon nucleus moving at near light speed, passing through brain tissue, causes physical disruption along the particle track. Not just diffuse chemical damage from ionization, actual structural disruption of the biological material it passes through. Axons can be severed along the particle track. Myelin sheaths can be damaged. The neurons along the track can be physically destroyed in ways that are not simply repaired by the body's normal cellular repair mechanisms. Animal studies with heavy ions similar to galactic cosmic rays have documented measurable cognitive effects at doses relevant to long-duration spaceflight. Impaired spatial memory, reduced performance on problem-solving tasks, increased anxiety and reduced behavioral flexibility, changes in the ability to learn new tasks. These are not subtle population-level statistics that barely reach statistical significance. They are measurable changes in the behavior of individual animals. Whether the same effects occur in humans at the doses encountered during a multi-year interstellar voyage is a question that existing data cannot definitively answer. We don't have human subjects who have been exposed to years of galactic cosmic ray radiation. The animal models provide reason for genuine concern, and the cognitive functions most sensitive to heavy ion radiation are precisely those most needed on an interstellar mission. Complex reasoning, adaptive problem-solving, spatial navigation, decision-making under novel and high-stakes conditions. These are the mental capacities that keep the crew alive. The radiation environment works against those capacities over time, not as a guarantee. As a growing probability with every additional year of exposure. Here's what happens when dust becomes a threat. At 10% of light speed, a particle with the mass of a single grain of sand, roughly 1 milligram, strikes your hull, with kinetic energy equivalent to about 108 kilograms of TNT. That's not a metaphor or an approximation for dramatic effect. That's the actual number. At 20% of light speed, that same grain delivers about 440 kilograms. At 50% of light speed, roughly 3,300 kilograms. The damage mechanism at these velocities is completely different from what you'd expect from a conventional impact. At relativistic impact velocities, both the projectile and the material it strikes vaporize, essentially instantaneously on contact. The kinetic energy converts to heat so rapidly in timescales measured in femtoseconds, quadrillionths of a second, that matter transitions from solid directly to plasma. The result is a superheated plasma jet that expands outward from the impact point with enormous velocity. Current spacecraft use Whipple shields, a thin outer bumper separated from the main pressure vessel hull by a gap. A hypervelocity projectile hitting the outer bumper vaporizes. The resulting cloud of plasma and debris expands across the gap and deposits its energy over a wider area of the main hull, reducing the damage that would occur from a direct impact. This works acceptably at velocities of a few miles per second, typical for micrometeorites in the inner solar system. At 10% of light speed, the energies are orders of magnitude higher. The plasma jet from a vaporized grain of sand carries enough energy after dispersing to punch through a standard Whipple shield configuration. More layers, denser leading-edge materials, magnetic deflection of ionized particles, All of these are part of proposed mitigation strategies. None are perfect. Magnetic deflection helps for ionized particles, hydrogen atoms, that have been stripped of their electrons. It doesn't help for neutral dust grains. Physical shielding is the only countermeasure for neutral material. And every kilogram of physical shielding adds to the mass the propulsion system must push. Over a crossing of 1 light year, a ship sweeps an enormous volume of space. Engineering for this hazard is not optional. It's fundamental. And it costs mass. Navigation across 1 light year demands its own examination. You are not following a road. There are no fixed landmarks in any conventional sense. Every reference point you might use is itself in motion. Stars orbit the galactic center. The Sun orbits at about 514,000 miles per hour, completing one circuit in roughly 225 million years. Other stars orbit on their own paths, at their own velocities and orbital inclinations. Over the years of an interstellar voyage, the positions of surrounding stars shift measurably relative to where they appeared when you departed. Navigation to a destination requires knowing where it will be when you arrive. Not where it appears from Earth, now. Not where it was when the mission was planned. Where it will be at the moment of your arrival. This requires precise knowledge of the target star's proper motion, its angular velocity across the sky, its radial velocity, the component of motion directly toward or away from you, and its distance, to convert angular motion into actual physical displacement. For nearby stars, we actually have this data. The Gaia mission, a European Space Agency astrometric satellite launched in 2013 and operational from 2014, has measured positions, proper motions, and distances for roughly 1.8 billion stars with extraordinary precision. Position predictions for stars within 100 light-years are accurate enough to serve as navigation targets over multi-year timescales. But navigation also requires knowing your own position and velocity at every moment throughout the journey. At relativistic speeds, the interpretation of incoming positional data must account for light travel time effects. Starlight reaching your sensors from a star left that star sometime in the past. The faster you're moving and the longer you've been traveling, the more the apparent position of a star differs from its actual current position. Correcting for this in real time requires onboard computation that accounts for all relativistic effects simultaneously. For absolute position fixing without communication with Earth, pulsar timing offers the most reliable method available. Millisecond pulsars, neutron stars, spinning hundreds of times per second, emitting beams of radio or X-ray emission that sweep past us with extreme regularity, serve as cosmic clocks. Their timing is stable to parts per quadrillion. By measuring the arrival times of signals from several pulsars simultaneously and comparing those times to precisely calculated predicted values, a ship can determine its three-dimensional position in the galaxy with high accuracy. This technique has been demonstrated in principle. Among all the challenges of interstellar travel, navigation is perhaps the most tractable. It is a problem of precision and computation. The physics does not actively work against you the way it does on the energy and biology problems. Communication is a different matter. The degradation of the link to Earth over the course of a 1 light-year voyage changes the fundamental character of the mission in ways that go beyond operational inconvenience. At departure, communications are nearly instantaneous. Ground support teams monitor every system. They can diagnose problems and suggest solutions in near real time. The crew operates in a familiar environment of constant connectivity. As the ship accelerates and distance grows, that connectivity fades. At 1/10 of a light year reached in under a year, at 10% of light speed signals take about 5 weeks each way. 10 weeks round trip. A question receives an answer in 2.5 months. This is workable. You plan for delays. But it's not the real-time support you had at the beginning. At 1/4 of a light year, 3 months each way, 6 months round trip. Real-time operational support is functionally impossible now. If a system fails and the crew needs guidance on an unfamiliar repair, Earth's response arrives 3 months after the request. The failure has either been resolved in that 3 months, or the situation has evolved in ways Earth doesn't know about. The crew is operationally on their own. At half a light year, reached after 5 years of travel, a 10% of light speed delay is 6 months each way. A year for any exchange. News from Earth is a year old when it arrives. The crew's reports to Earth describe conditions from 6 months ago by the time they're read. This is not communication in any meaningful present tense sense. It is the exchange of records. At 1 light year, signals take a full year in each direction. 2 years for any exchange. A distress call sent from 1 light year takes a year to reach Earth. Earth's response takes another year to return. 2 years minimum between when you describe a problem and when you might receive guidance about it. The guidance arrives 2 years after the problem was described. Current conditions will have diverged from those in your description. The guidance may or may not still apply. This is what communication at 1 light year means. Not slow, not delayed. Fundamentally different from any form of communication with Earth that provides real operational support. The further you go from Earth, the more completely you are on your own. 1 light year is the distance at which that aloneness reaches its practical limit. Now consider what lies at the destination. After years of transit, after weeks of subjective time at near light speed, you've crossed 1 light year. You are not at a star system. The nearest stars are still more than 3 light years away. Proxima Centauri, the closest star to our Sun, is at 4.24 light years. Alpha Centauri A and Alpha Centauri B, the 2 Sun-like stars that Proxima orbits, are at about 4.37 light years. 1 light year places you in the interstellar void between our solar system and the nearest stellar neighbors. In the middle of the gap, there is no planet, no moon, no asteroid belt, no atmosphere, no magnetic field providing any radiation protection, no solar wind, no meaningful starlight for energy. The sun behind you has shrunk to a bright stellar point, still the brightest star in the sky by a substantial margin, since you've traveled straight away from it, but providing no warmth or usable energy at this distance. The boundary where the sun's wind gives way to the interstellar medium is called the heliopause, and it lies at roughly 100 astronomical units from the sun. 1 light year is 63,241 astronomical units. You cross the heliopause very early in the journey, in the first fraction of a percent of the total distance. And that crossing, that moment when you left the sun's solar wind behind, marks the beginning of the Oort cloud. Most people are unaware that the solar system extends as far as it does. The familiar solar system, the Sun, the 8 planets, the asteroid belt, the moons fits within Neptune's orbit at about 30 astronomical units from the Sun. Beyond Neptune lies the Kuiper belt, a ring of icy objects extending from about 30 to 50 astronomical units. Pluto is a Kuiper belt object. The Kuiper belt gives way to the scattered disk, a sparse region extending to several hundred astronomical units. And then, much further out, the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies surrounding the entire solar system. Its inner edge is estimated to begin somewhere around 2,000 astronomical units from the Sun. Its outer edge extends to perhaps 100,000 astronomical units. This is the region that long-period comets come from bodies with orbital periods of hundreds or thousands or millions of years, perturbed by gravitational encounters with passing stars and sent tumbling inward toward the Sun on elongated orbits. 1 light-year, in astronomical units, is 63,241 astronomical units. This puts the outer edge of the Oort cloud at roughly 1 light-year from the Sun. The solar system doesn't end at Neptune. Its gravitational influence and the population of bodies bound to it extends to approximately 1 light-year. The first light-year of any interstellar journey is, in a real physical sense, the crossing of our own solar system's outermost territory. You wouldn't cross it and arrive somewhere new. You'd cross it and arrive at the boundary between our Sun's domain and the true void. At the outer edge of the Oort cloud, looking back, the Sun is still the brightest object in the sky. Still clearly identifiable. Still gravitationally dominant over everything around you. But distant. 63,000 times further than Earth is from the Sun. A point of light, not a disk. And looking forward, in any direction that isn't toward our own star, the nearest stellar systems are still more than 3 light-years away. The void between us and them belongs to no star. It exists because stars are rare and space is vast, and the universe was built at those proportions. Surrounding you is gas at average density of 1 atom per cubic centimeter. The ambient temperature of the environment approaches the temperature of the cosmic microwave background radiation, roughly minus 455 degrees Fahrenheit, just a few degrees above absolute zero. Every photon of warmth inside the ship was generated internally. The reactor, the electronics, the biological heat of the crew. Managing thermal equilibrium, keeping the interior at survivable temperatures, requires careful thermal engineering of the hull and continuous power generation. And here, at this point, 1 light-year from Earth, is where the isolation becomes most concrete. A signal to Earth takes a year to arrive. A response takes another year. Any news from Earth reflects the world over a year ago. If something goes wrong right now, there is no rescue that could reach you in any time frame that matters for an emergency. A rescue mission launched immediately upon receiving your distress call would take a minimum of another year just to receive the call. Years more to prepare and travel. Nothing could reach you in time to matter for any acute crisis. You are on your own. The ship, the crew, the knowledge and supplies aboard. Every decision here is made by the people present with what they have. There is no one else. There is also a thermal engineering problem at 1 light-year that is easily overlooked. The ship is not in sunlight in any useful sense. At 1 light-year from the Sun, the intensity of sunlight has dropped to roughly 1/4 billionth of what it is at Earth's distance. Solar panels that generate hundreds of watts per square meter in Earth orbit would generate a fraction of a watt per square meter at 1 light-year. Useless for anything practical. The ship is thermally isolated from any external heat source. Every watt of heat aboard the ship is generated internally. The crew generates heat through their metabolism, roughly 80 to 100 watts per person at rest. The electronics generate heat through their operation. The reactor, whatever power source the ship uses, generates heat as a necessary byproduct of energy production. All of this heat must be managed. In space, the only way to shed heat is through radiation. A surface at a given temperature radiates heat at a rate proportional to the 4th power of that temperature. The radiators of an interstellar ship must be large enough to shed the ship's waste heat at a rate that keeps internal temperatures survivable. But radiators are mass. Large radiators are a lot of mass. And mass is the central problem. Every thermal engineering decision aboard an interstellar ship is a negotiation between survivable internal temperatures and the mass cost of the radiators needed to achieve them. The external temperature of space, defined by the cosmic microwave background radiation, is -455 degrees Fahrenheit. This actually helps. The huge temperature difference between the ship's radiating surfaces and the ambient environment means radiators can shed heat efficiently, even at moderate sizes. But this requires the radiators to see that cold background to have unobstructed views of deep space, rather than being partially shadowed by other parts of the ship. Ship geometry becomes a thermal engineering constraint as much as a structural one. The human dimension of time dilation is something the physics describes precisely, and the experience would make profound. A crew member leaves Earth. They have people they care about. A life built over years. They accelerate to 99% of light speed. Their subjective crossing of 1 light-year takes about 52 days. During those 52 days, the people they left behind age through over a year. A parent is a year older. A child has grown by a year. Events have occurred, ordinary and extraordinary ones, that the crew member missed. Not because they were distracted, not because they were careless, because their relationship to time was physically altered by velocity. They aged 52 days. Everyone else aged over a year. When they return, if they return, the gap is real and permanent. There is no way to reverse it, no way to reconcile it, no way for everyone to end up having aged the same amount. They lived different quantities of time. One of them has more past than the other. The cells in their bodies reflect this. The state of their biology reflects this. The universe recorded the difference with perfect precision. This is what traveling 1 light-year at near light speed means at the human level. Not just a change in location, a step out of sync with the rest of your species. A return from somewhere, but also from somewhen. The person who steps off that ship is measurably younger than they would have been had they stayed. Not in some philosophical sense. Measurably. Biologically. In terms of the number of times their cells have divided. In terms of the state of their DNA repair mechanisms. In terms of how much aging their telomeres have undergone. That's not sentiment. That's the physics. And the physics has been right about this every time it's been tested, at every accessible scale, without exception. The return trip, if there is one, adds its own layer to this temporal displacement. You travel 1 light year away at 99% of light speed. You experience 52 days. You stop at your destination. You spend some time there, days, weeks. You accelerate back toward Earth at 99% of light speed. You experience another 52 days on the return leg. You arrive at Earth approximately 2.5 years after you left, measured in Earth time. You have aged about 110 days. Your friends have aged over 2.5 years. A child you left when they were 10 years old is now 12.5. A parent who was in good health when you launched has experienced more than 2 years of aging. Events that shaped the world during your absence are things you know only from the messages that arrived during the voyage, delayed descriptions of things that happened before the messages were sent. Your physical experience of those 2.5 Earth years is 110 days. A season, roughly. The cognitive dissonance of returning to a world that has moved on without you, a world that is 2.5 years older, while you are barely 3.5 months older, is not a simple thing to process. You are the same person. The relationships you had before you left are still real, but the shared timeline has fractured. You and the people who love you have lived through the same 2.5 years of history, but at different rates. You experienced a slice of it. They experienced all of it. The gap is permanent. It cannot be repaired by conversation or explanation. It can only be acknowledged as the physical consequence of the journey you chose to make. The universe doesn't make exceptions for emotional attachment. It applies the Lorentz factor uniformly, without consideration for what it costs the people on either end. The people left behind have their own experience. You watch a ship launch. You know the people aboard. You know they're traveling at velocities that make time run differently for them. Over weeks and months and years, you adjust to receiving messages from the past. News from the ship is old news. You respond to their questions, knowing your response will arrive over a year after they asked it. You respond to their descriptions of events that occurred over a year ago from your perspective. You have no access to what's happening on the ship right now, only to what was happening there over a year ago. The ship is out there. The crew is presumably alive, but you're not in contact with them in any present tense sense. You're corresponding with their history. They're corresponding with yours. When they return, after their 52 subjective days, after your 1.5 years of waiting, the gap is visible. Not dramatically, not decades of difference, but real, confirmed by comparing clocks, by comparing biological markers, by comparing the number of times cells have divided. The people who traveled are measurably younger. The people who stayed are measurably older, by exactly the amount the Lorentz factor predicts. The universe is precise about this. Completely, inflexibly precise. It gives you the exact result for any velocity you specify. And that result is not negotiable. There's something worth recognizing about what the act of calculating this journey reveals. We are capable of precisely describing a voyage we cannot make. We can state every consequence of crossing 1 light year, the exact time dilation, the exact radiation dose, the exact Doppler shift, the exact energy cost with quantitative precision. We can know, in detail, what would happen to human biology on a decade-long voyage at 10% of light speed. We can know what the sky would look like at 99% of light speed. calculate the aberration angle, predict which stars would shift into visible wavelengths from the infrared, describe the exact hue of the compressed cosmic microwave background. All of this knowledge exists. None of it has been gathered from anyone who has made the journey. It has been assembled from 4 centuries of physics developed on the ground, from Galileo's inclined planes to the Large Hadron Collider. From observations of phenomena, the equations predicted before those phenomena were detected, gravitational waves, black holes, cosmic microwave background polarization, binary pulsar orbital decay. From experimental verification of time dilation in particle accelerators and atomic clock experiments. From half a century of human spaceflight data, continuously refining understanding of how biology responds to the space environment. From satellite operations that depend on relativistic corrections being exactly right. From robot probes in interstellar space, the Voyagers providing direct measurements of the environment beyond the heliopause. All of it assembled into a picture detailed enough to describe, in advance, what would happen to a crew crossing 1 light-year. That's not a small thing. That's science, functioning at its best. Building knowledge systematically over centuries until it describes phenomena beyond the reach of any individual or any generation to directly observe. Think about what it would mean to be the generation that builds the first interstellar capability. Not the generation that crosses 1 light-year. The generation that achieves the propulsion, the biology management, the shielding, the power generation that makes the crossing possible. That generation will not be the one that goes. The engineers who solve the propulsion problem might not live to see the mission launch. The biologists who work out the long-term physiological countermeasures might not see the crew they helped keep alive. This is not unique to interstellar travel. The physicists who developed the theoretical foundations of nuclear energy died long before the technology reached its current scale. The mathematicians who formulated the equations of orbital mechanics lived centuries before the first spacecraft flew. Science builds across generations. Always has. The knowledge doesn't belong to the people who generated it. It belongs to everyone who comes after. We are currently the people who come after several centuries of physics development. The understanding we have of what 1 light-year requires comes from thousands of people across hundreds of years who asked precise questions and recorded precise answers. We didn't generate the physics ourselves. We inherited it. The next generation inherits what we add. And what we add is not nothing. Space station data on long-duration physiology. Precision measurements from the Gaia satellite, improving our knowledge of stellar positions and proper motions. Particle physics at the Large Hadron Collider, deepening understanding of matter at relativistic energies. Advances in materials, science toward lighter and more radiation-resistant structural materials. Progress in compact fusion concepts. Each of these narrows the gap between current capability and what 1 light-year requires. The gap remains large, but it is not the same size it was 50 years ago. And it will not be the same size 50 years from now. Here is what we have, without having made the journey. We can describe it in precise, quantitative, testable detail. We know the time dilation factor at every velocity. We know the Doppler shift that transforms the apparent color of every star. We know the aberration effect that crowds the universe's light into the forward disk. We know what the interstellar medium does to a hull at 10% and 50% and 90% of light speed. We know the rate of bone loss in microgravity from 6-month missions. We have models extrapolated for longer durations. We know the radiation dose rates in deep space and their cumulative biological effects. We know the communication delay at every point along a 1 light-year route. We know the navigation mathematics and the pulsar timing methods that make positioning possible without Earth contact. We know what time dilation means for the crew and for the people left behind. None of this knowledge comes from having made the journey. It comes from physics developed over 4 centuries, tested in laboratories, particle accelerators, atomic clocks, and orbiting satellites. From observations of phenomena, the equations predicted before those phenomena were observed. Muon decay at exactly the rate the Lorentz factor says. GPS clock drift at exactly the rate relativity predicts. Gravitational lensing, bending light exactly as general relativity calculates. Binary pulsar orbital decay exactly matching the prediction from gravitational wave emission. The universe keeps returning the same answer because there is only one answer. The physics isn't a working hypothesis. It's a description of how reality actually behaves. Every test, every measurement, the physics is right. The GPS in your pocket depends on relativistic corrections calculated from the same equations that describe a 1 light-year voyage. If those equations were wrong, the GPS would be wrong. It isn't. The muons on Earth's surface are present in exactly the numbers the Lorentz factor predicts. If the prediction were wrong, the muon count wouldn't match. It matches. Every time. These are not separate coincidences. They're the same physics, tested in different circumstances, always returning the same precise answer. We tend to think of interstellar distances as obstacles, as barriers between us and places we want to be. But the distances are also information. They tell you something about the structure of the universe, about how matter collapses under gravity into stars, how those stars cluster into galaxies, how those galaxies are distributed across space, and therefore how often stars end up near each other versus how often they end up separated by years of light. The average distance between stars in our region of the Milky Way is about 4 to 5 light years. Not in every direction. The galaxy is not uniformly distributed. There are denser regions and emptier ones. Star-forming regions can have stellar separations measured in fractions of a light year. Globular clusters pack hundreds of thousands of stars into a sphere a few hundred light years across. But in the local stellar neighborhood, the region within a few dozen light years of the Sun, 4 to 5 light years between neighbors, is roughly average. This is telling you something about the physics of star formation. Stars form from the collapse of molecular gas clouds. Those clouds fragment as they collapse, with each fragment producing a protostar. The scale of the fragmentation is set by the physical properties of the cloud, its temperature, density, and the strength of its magnetic field. The typical separation between resulting stars reflects these initial conditions. The universe made stars at the scale and density that the physics of cloud collapse produces, not at human-friendly spacing. Not at distances where nearby interstellar travel would be routine, at whatever separation the physics dictated. And the physics dictated separations of light years. The universe is not hostile to life and exploration in any deliberate sense. It is simply structured according to its own physics, which is indifferent to biological requirements or travel convenience. 1 light year, just one, a fraction of even the nearest stellar gap requires everything we've described. The full stellar gap to Alpha Centauri is 4.2, 4 times that. These are not metaphors for difficulty. They are the actual distances, with the actual costs attached to them, governed by the actual physics. The universe is what it is. We exist inside it. And everything we learn about crossing it starts with being honest about what it contains. So, what actually happens when you travel 1 light year? Time dilates. The sky transforms stars crowded forward into a blazing disk, colors shifted beyond recognition, the relic radiation of the Big Bang itself made visible by your speed. The interstellar medium becomes a particle radiation environment requiring engineering that adds mass and compounds every other cost. Dust grains become hypervelocity projectiles with explosive equivalent kinetic energies. The body loses bone density, muscle mass, cardiovascular conditioning, and possibly some visual acuity in microgravity over years, unless mass-expensive countermeasures are maintained throughout. Cosmic rays accumulate in tissue and brain matter over years, adding to a statistical ledger of biological risk that never stops growing. Communications with Earth degrade from conversation to correspondence to historical archive, receiving records from a civilization that has moved on while you were traveling. Navigation requires knowing where your destination will be in the future, not where it appears now. The energy required to accelerate and decelerate a crewed ship exceeds by orders of magnitude the total energy humanity currently produces in a year. And at the end of it, if you've traveled at near light speed, you arrive having aged weeks, while Earth has aged over a year. Displaced in time as surely as in space. Every one of these consequences is real. Every one is described by physics that has been verified at every accessible scale. None of it is speculation. It is the universe being precise about what crossing 1 light year requires. And what it requires is more than we currently have. That will change. The history of technological progress is long enough and surprising enough that dismissing future solutions would be premature. The antimatter production problem is not forbidden by physics. It's a scale and efficiency problem. Physics allows antimatter. Physics doesn't restrict how efficiently it can be produced. Better accelerator designs or entirely new production methods could in principle close the gap between nanograms per year and kilograms per year. The rotating habitat for artificial gravity is not exotic. It's a structural engineering challenge. The biology questions about long-duration spaceflight will be answered by long-duration spaceflight. We answer biology questions by going and observing and adapting. What's genuinely unknown is whether there is a solution to the fundamental energy problem that doesn't require energy inputs that are physically staggering. Not whether better solutions exist. Whether solutions that are actually practical, at the scale of civilizations rather than planets, exist within the constraint of known physics. That's the honest unknown. Not whether humans will ever cross interstellar distances. But when, and at what cost? And whether the cost is one that any civilization can realistically pay, or one that requires a kind of civilization we cannot yet imagine. And that is how all of science works at its frontier. Precise about what it knows. Honest about what remains open. The universe doesn't owe us answers on a time scale that fits human lifetimes or human ambitions. It offers its structure to anyone willing to look carefully enough. We have looked. We have been looking for 4 centuries. And what we have found about the cost of crossing 1 light year is not discouraging. It is honest. The physics answers every question you ask it, precisely. It just doesn't answer that one. That one is still open. The civilizations that someday cross 1 light-year will build on what we've already understood. They won't discover that time dilates. They'll be managing exactly how it dilates. They won't be surprised by the radiation environment. They'll have solved the shielding. They won't be unprepared for the biology of long-duration spaceflight. They'll have solved artificial gravity and the other countermeasures. They will know what the physics demands, because we worked it out here. From the surface of a small planet, with equations and experiments, and a willingness to follow the physics wherever it leads. Even when it leads somewhere we cannot yet go. Even when the honest accounting is humbling. The next time you look up at a clear night sky and find a bright star Sirius at 8.6 light-years, or Vega at 25, or the concept of Proxima Centauri at 4.24 light-years. Those numbers aren't just large. They are the measure of what the universe actually is. How much of it there is between the things that shine. How much emptiness separates the points of light. 1 light-year of that emptiness, just one, would require a civilization's worth of energy to cross with human beings aboard. And it wouldn't even get you to anyone. It would put you in the middle of the gap. In the cold, particle-thin, radiation-bathed, utterly isolated void between solar systems. With a year of light travel, in every direction, for any signal you send. On your own, in the fullest possible sense of that phrase. That's what the distance actually is. Not a destination. A demonstration of what the universe is made of and how much of it there is. And the fact that we can calculate every consequence of that crossing, the exact time the crew ages versus Earth, the exact color shift of the stars, the exact rate of bone loss, the exact energy cost, that's something. That's the product of 4 centuries of people asking precise questions and accepting precise answers. Even when the answers describe a journey none of them could make. Even when the answers are humbling. We know what it costs. We know what it does. We know what it looks like. We're ready to understand it. And that's where every great journey starts. If this kind of deep and honest examination of what the universe actually requires is what brings you here, a like or subscribe helps this channel keep going. Thank you for making it through all of it. Good night.